Hey guys, welcome back to my Java tutorial series. This is lesson 10, where we will be covering the 8 primitive types. We will also cover why strings are not one of the 8 primitive types. But without further ado, let's get into it. So in Java, as we learned with our variables, every number or data item that the computer processes has a value, and every value has a type. So numbers can either be integers or floating point. An integer is a whole number, while a floating point number can have a fractional or a decimal part, although the fraction is frequently represented, not frequently, but is always represented by the computer as a decimal. So we're going to start off with some types that we've known, which are ints. So I'll make an int here, or an integer. Public int, we'll call it num, and that can be 4. So when you see a value such as 4, that is called a number literal. Never use commas to write number literals. Like if I want to do 4,000, I'm not going to do 4, comma 000 like I would when I'm writing. Instead, I'm just going to do 4,000, just the digits. Because Java and I think nearly all programming languages that I know of can't process a comma as a number, unlike our human brains. So if we have a number that's large like this, or even larger like that, we can use scientific notation. So if I wanted to write the number 8.723 times 10 to the 7th, like let's say I wanted to write this in Java, I wouldn't write out all of this because, as you can see, it has no idea what is going on. So instead, what I'm going to do is I'm going to write down my 8.723, and then I'm going to go E7. And I think it has a problem. Yeah, and I'm going to have to change this to a double. So that brings us to my, not mine, sorry. Actually, yeah, I'll go with this. My second point, which is doubles, or the second primitive type we're going to be looking at. And the reason we couldn't use this as an int is because of this decimal point. However, we can store it as a double. And we can also store like pi as a double, 9, whatever. We can store pi as a double. We can even store an integer as a double. If we did want to do that though, I'd recommend just doing this 9.0, just so that readers can know, like if you're working on a team like that, your team members can know what exactly num means, like without having to go back and find out where it's declared, like right here. I mean, when it's short like this, go for it. When you're on your own, go for it. It's probably just best to get into good programming practices. Okay, so there are also other ways that we can store both integer and floating point numbers. And the reason for that is because each one takes up a different amount of space. So an int will take up 32 bits, which is 4 bytes, and a double will take up 64 bytes, or 64 bits, which is 8 bytes. So, like, let's say we just wanted to store a really small number, like 5. Luckily for us, there are multiple variations for integers and floating point types. The smallest one for an integer is what's called a byte, and that takes up 1 byte of data, or 8 bits. And this can go from -2 to the power of 7 to +2 to the power of 7 minus 1. So that goes from -28 to 127. Wow, that's way too large. To 127. So what's interesting to know here is that this is 2 to the power of the amount of room it takes, 8 bits, minus 1. And then that's also minus 1 for positive, or not like that for 0, or for negative. And that's because this includes 0. So like if we wanted to just go -1, we can go -1 to -128 because that is just 2 to the 7. That's just 2 to the 7 points of data. However, we have to include 0 somewhere because all numerical primitive types have a default value of 0. So it needs to be included, and it's included with the positive. So we'll see this with the other integer primitive types. Like we'll see that it goes from -2 to the power of the amount of bits minus 1 to +2 to the power of bits minus 1 minus 1. So we can do like a public byte, and we'll call this just small num, and I don't know, we'll make it 4, and then I suppose we should include the int here, public int num equals 1938. But let's say that we wanted to do something larger than +127, but we didn't want to take up 32 bits of computer memory. We're also in luck because there is this thing called a short. And a short can store 16 bits of data, and its values go from -2 to the 15th, or 2 to the 16 minus 1, to +2 to the 16 minus 1 minus 1. Because it's relatively small, I'm just going to say that it's -32,768 to +32,767. So I could say a short will be, we'll go with 30,000. That is way too much. 30,000. Oh, and I never called it something. Short, I suppose. I'm not very creative today. And just to show that ints can take up a little more, we'll make that a bit larger. However, if we're dealing with large numbers, we can't use an integer. Like let's say that we're dealing with a number that exceeds 2 to the 32, because an int is 32 bits, 2 to the 32 minus 1 minus 1. Or, in the negative direction, -2 to the power of 31. Let's say that we wanted to do something bigger, like, I don't know, we wanted to do 2 to the power of 40. What we would use then is what's called a long. We'll do large num equals 3, I'll just add a bunch of zeros. Now, notice that I put an L at the end of this, a capital L. This denotes long. This tells us, okay, we're dealing with a number of type long. We're not dealing with an integer. This can be manipulated with other big numbers to make an even bigger number, or if you're subtracting, it can be a little bit smaller, but we're mainly focusing on the fact that this can store 64 bits of data. And this goes from -2 to the 63rd, or 2 to the 64 minus 1, to +2 to the 63rd with that minus 1 at the end, of course. So that can store a lot of stuff. And now we're going to move into floating points. So the first one is called float, which is very nice and descriptive. We'll just do floating num. And we'll just start it off with pi, 3.1415926. However, we can't leave this number like it is, because that will get confused with a double. So in order for the computer to know that we're dealing with only a number with a maximum of 32 bits of data, we have to put this f at the end. And then, as we did earlier, double. I'll just call this number. I'm really creative today, I know. We'll store the same thing, 3.1415. Oh, wow, that's an 8. I'm sorry. 926. So as you can see, they store the same value, but because this has an f at the end of it, the computer only uses up 32 bits of space. However, for this one, the double, the computer uses up 64 bits of space. So as you can see, it can be advantageous to use floating points, and it can also be advantageous to not just use ints exclusively, but start to use a variety of these types so that you can be economic with the amount of memory that you take up. Of course, when you're dealing with rather small programs and you're not manipulating large amounts of data and you don't need to do like these crazy fast calculations for some reason, I'm just throwing out examples here. But let's say you don't need to do any of that. You can just use int and double. It's not going to have any impact on your compiling speed. This is really only for like when you need nice quick compiling because you have a lot of stuff to compile. So now we're going to get into the funky ones. We did the number ones. They are the first 6. They're very nice and easy. But then it gets a little weird. We're going to store some characters, and this is called the char type. I think it's pronounced char. It might be char. I've heard people use both. I use char because it's short for character. If it's actually pronounced char, just please let me know in the comments so I can, correct this. And so I'm not also saying it wrong for the rest of my life. But in any case, we'll just call this letter. And a char can take any, I don't know what, like, I don't know if there's like a fancy word for letter, like lexicographic. I don't know, I'll just call this, it can take letters. If you need to store letters or just like a digit as a letter. Like if we don't want to manipulate 7, we just want to like print out 7, we can do that. And then of course we need a semicolon. But let's just store A. Let's just set it equal to A. That's how we can store a single letter. However, we can also do the fancy letters. Like I'm from the United States, so I have a very finite keyboard. But if you're from I don't know, nearly anywhere in Europe, you're gonna have like you might have the A with the 2 dots over it, or like the O with the stroke, and you might need to be able to print out those. Luckily, you can. If you do /u and then a specific 4 digits following that, you can actually print out any letter you want. So the U denotes Unicode, and that's what these are. These are called Unicode characters. And luckily for us, the internet has a fun table with all of them. So let's print out something fun. I don't know. Here, this one looks interesting. So this is U0126. It's an H with what appears to be a slash through it, or a strike through. So, and I just forgot the number. I think it was 01. Yeah, there we go. Whoops. 0126. Let's say I want to print this out. System.out.println letter. Oh yeah. There we go. Print it out. And because Eclipse has no idea what we're talking about, that gets printed out instead. Let's do something that Eclipse will recognize, like a big G. 0047. Alrighty, let's try that one. There we go. Alright, so as you can see, you can use Unicode. If you're working on like a different compiler, if you're in Europe, for example, and you're working on a different compiler, maybe it'll actually print out. Maybe it'll print out a European one. Like let's do the ash. I think it's ash letter 00C6. So you might be confused by why there is a C in here, but that's because this stores it as hexadecimal. I'll include a link to both this table and a breakdown of hexadecimal in the description below. But basically hexadecimal is base 16. You can store, you got your 10 digits, and then you can do 11, 12, 13, 14, 15, 16 with A, B, C, D, E, and F. So that C means this is what, 13, right? Yeah, 13. But like it doesn't actually matter because it's just a way to store different things. So now we'll print that out. Oh, sweet. All right, so it does print out European characters. I don't think it prints out these fancy ones that I've never seen used anywhere in the world. But, for all I know, they might be. Alright, so that was a fun tangent. yeah, that's Unicode characters. They're pretty simple. The last one is also, actually I'd call it the simplest, um, because it has two values, true or false, and this is called Boolean. So we'll do Boolean statement because it stores a true/false statement. We'll just call it that. And I'm not going to set it to anything. Sorry. Now, by default, Booleans take a value of false. But I could also just set it to, I could, for people that did C++, you'll probably just set it to false, um, like on, I don't know, sorry, I'm drawing a blank here. Automatically. There we go. Because C++, for those that don't know, it doesn't instantiate your variables immediately like Java. But like, let's say I'll just make it true for now. Um, and on the topic of default values, all of these are, actually I'll just write down their default value here. So that's going to be 0. That's going to be 0. That'll be 0. I hope you're recognizing the pattern here. um, Actually, the pattern breaks a bit with the floating point because it needs to recognize that this does have a decimal, so it just does it 0.0. But for any number, it defaults to 0. And then this one defaults to U 4 zeros. I'm going to print that out. I can't remember on the top of my head what that is. Oh, all right, it's blank space. Perfect. Whoops. And then this one, that is not how I do it. There we go. All right, so that's really useful for something we'll learn later called a conditional. Like, if this is true, then do this. That's basic logic, and they're very useful. Chars are useful for something I'm sure that otherwise that wouldn't be a thing, but like I've never really used them. But if you don't want to store anything in a string, if you just have like one letter, I'd probably just use a char. So I actually made a table with these 8 primitive types and some other data about them. Let's go to here. There we go. So we have our 8 primitive types, description of values, default value, their size, and example literals. So I made a mistake here. I didn't actually include the F. Like for long I included that L, but for the float I didn't include the F. The F is required. For long you can get away without doing that, I think. Oh no, alright. You can't. Sweet. Alright, you have to do the L, and you have to do the F. I'll prove that to you in case you don't believe me, but here we go. It needs a cast of double. So I know I said I said earlier that string was not one of these, and they're very useful, very versatile, but they're not a primitive type because they're actually an object. A string is an object that consists of a collection of characters. So if I wanted, I can break a string down into different letters, but I can't break any of these down into a more basic component. Now you might argue, oh, well, what about a long? I can break that into a bunch of bytes. Like, yes, technically that's true, but you can't actually break a number down into anything more basic that a programming language can recognize. So I think that actually that concludes it for today. I don't have anything else, which is great because I don't want this to get too long. I think it already is long enough as is. But I'll include a link to this in the description below. I made a Dropbox for it, and also include a link to here, just in case you do find yourself, using this for something or another, and you need to know oh, what's division? It's 00F7. Great, type away at that, put it in there. So that concludes today's lesson, and I'll see you guys later.